So let us now apply the theorem that the work done by non-conservative forces is MEF minus MEI to some problems. The first one is, it's a simple problem. What we have is a block of 0.5 kg block compresses a spring constant 150 newtons per meter by an amount 0.08 meters. Okay, so the block is at rest and it is released. Now when it's let go, the spring pushes this block. Now once this block is completely out of touch with the spring, then it starts to slide on a rough surface. The coefficient of friction being kinetic friction is 0.5. And our question is, how far does it travel? So how far does it travel on the surface? Okay, so at this point, stop, pause the video, and see what you can do. Okay, come up with a method, and then see if you can get the same answer. If not, then go ahead a little bit, see what I'm doing in the video, and once again at regular intervals stop and ask if you can proceed with the problem. So here's what I'm going to do. I'm going to apply the work done by non-conservative force is equal to the change in the mechanical energy in the video. So let's see how to apply this. So in order to do that, there are three components. One is we have mechanical energy initial, mechanical energy final, and then we have the work done by the non-conservative force. Now in this case, we have two objects that the system is made up of, which is the spring and the block. For the block, we have kinetic and potential. For the spring, since we are only dealing with massless springs, we only have to worry about the spring potential energy. So keep that in mind. Okay, so that just simplifies life. So let's first find out MEI. In the beginning, so this MEI is going to be the ME for the block plus ME for the spring, all in the beginning. Now, what we know is that the block has both KE plus PE. So KE block plus potential energy of the block, which is gravitational potential of the energy of the block in the beginning, plus the spring only has potential energy. So I'm just going to write the potential energy for the spring. It has no mass, so kinetic is 0 for the spring. Alright, so since the block is not moving, its kinetic energy is 0. Since there is no change in height of the block, we can assume that its potential energy is also 0. It doesn't really do anything to the problem. The spring, on the other hand, is compressed, and so it has potential energy. So it is equal to 1/2 times 150 times 0.08 squared. Great. So we have this. We can calculate this number and we can figure out what the mechanical energy initial is. Now, let's figure out what happens at the end. In the end, what we know is that the block has stopped moving. So it has 0 kinetic. Its potential is 0. And the spring is no longer compressed or stretched. So the spring also has 0. So the mechanical energy final is simply 0 plus 0 plus 0. Okay, once again, the block is not moving. So the kinetic is 0. The potential energy is also 0 for the block. And the spring is unstretched, so its potential energy is 0 as well. So the final mechanical energy for the system in this case, in this problem, is simply 0. Great. So we're one step closer now. Now, let us figure out the work done by the non-conservative force. Now, in this case, draw a simple diagram here. As the block slides on the rough surface, what we have is we have friction that is pulling it to the left, and that force is simply mu k times Fn. The weight is 0.5 times 9.8 for the block. The contact force happens to be equal to the weight in this case because there are no forces along the vertical direction. And what we have is we have the work done by friction. That will be written as mu k times Fn, which is the force of friction, multiplied by this distance that it's traveling, which we do not know. So d is the unknown, multiplied by cosine of 180. Now this is important. Make sure you get that. Once we have this, let us figure out everything else. Mu k is simply 0.5 in the problem. multiplied by 0.5 times 9.8 times d times minus 1. So we have now all the components of our system. 0.5 times 9.8 is 4.9. That multiplied by 0.5 is 2.45. So we have negative 2.45 d as the work done by non-conservative forces, and we can now plug it into the equation and have negative 2.45 d equals 0 minus 1/2 times 150 times 0.08 squared. That's it. And from here we can solve for d. You can go ahead, calculate the value of d, and make sure that you get the correct answer. So if you do it all correctly, you'll end up getting, for the distance traveled, 0.196 meters. So that's our answer. Alright, in the next video we'll look at something more involved.